And here we go. Okay, so guys, the topic for the day today is molecular polarity. Normally when we start this unit, I spend 5 or 10 minutes and explain to you why this is going to be your favorite unit all year, because typically this is students' favorite unit all year, because we get to talk about things like why does sugar not dissolve in gasoline, and how did that start the eco-terrorism movement down in Moab, Utah. But we're not going to talk about that now because you're going to forget. So we'll talk about that when we get back after Christmas break. You guys all knew that, right? That sugar doesn't dissolve in gasoline, and as a result, if you pour sugar in the gas tank of things like bulldozers, those bulldozers start and then die, and that was the whole start of Greenpeace and Earth First and the eco-terrorism movement, which started in Moab. Do you guys not know anything? No. Edward Abbey? Do not go home over Christmas break and get Edward Abbey books and read them because your parents will kill me because the language is horrible. But all of Edward Abbey's work was actually done as he was a park ranger down in Arches, down in Moab, and he actually started in the 60s the eco-terrorism movement. There you go. All right, so guys, with all of that said, guys, what we're going to do today is we are going to build the foundation upon which we can start asking some really interesting questions like sugar and gas, which wouldn't be interesting other than it's actually interesting. But guys, in order to do this, we've got to today talk about something called molecular polarity. So the date today is the 15th, and let's talk. So guys, don't write this down, but this is what we're going to do today. We are going to, first of all, go back really quick and make sure that you guys can all draw Lewis dot molecular structures, but I already know you can because you did well on the test. So we're going to sort of touch that quick. Then guys, what we're going to do is this. We are going to learn, and this is sort of new, we are going to learn how to connect the Lewis dot structures that you know how to draw with what they actually look like three-dimensionally. And guys, just so you understand, that's why we put this part on the test. So this is the test you just took. That's why we put this part on there. And you guys actually did pretty well with this. Just a second. Guys, that's why we put this on the test, because after having done the lab, you have a general sense of what these look like three-dimensionally. We're going to tie into that today. Go ahead. Yeah. Carbon cannot be pyramidal. Carbon tends to be flat or tetrahedral, or linear in the case of carbon dioxide. But yeah, carbon typically does not become trigonal pyramid. Anyway, okay, so then guys, what we're going to do is we're going to talk again very quickly about symmetry. We're going to tie these three ideas together. Remember, we talked symmetry in the lab. The thing that's going to make this a little different is you're going to have to be able to determine symmetry without having the molecules in your hand. Then guys, we're going to go back to the second day of the previous unit. We're going to talk about polar and nonpolar covalent bonding. If you remember, we learned that in the previous unit, and I said don't worry about it until the next unit. Well, now is the next unit. And then guys, we're going to bring all of this together. We're going to talk about molecular polarities, and you're going to get your homework done. Ready to go? All right. Good? Good? Yeah, you guys are good at this. So guys, when we talk about drawing Lewis dot molecular structures, we are talking about this process. We're talking about putting all the atoms on the paper. We're talking about drawing them symmetrically. We're talking about carbon in the middle. Ooh, this one, guys, a couple of you forgot about this on the test. Hydrogen and the halogens cannot be in the middle. Remember that. And then guys, we counted valence electrons, we spread out the electrons, we checked the octet rule, we drew Lewis dot structures. Remember all of that? Okay, so now guys, and I don't think you want to write this down necessarily, but what I want to do is I want to go back and talk about these Lewis dot structures. And I don't want you to draw these, but guys, what I do want to do is show you how we're going to draw these maybe a little bit differently. So guys, for example, CCl4. Can you picture in your mind what this is going to look like? Where does the carbon go? In the middle, right? And then when you start spreading the electrons around these chlorines, you're going to fill in all of the chlorines first because they are halogens and they've got to get filled up first. And you would probably then draw, why is my clicker not working? Draw something like this. Can you sort of picture that? What's the domain geometry if it's got 4 domains? Tetrahedral. The molecular geometry, because they're all bonding domains, is also tetrahedral, and it's 109.5 degree angles, and oh my gosh, there it is. It looks like this. You okay? Okay, so guys, here's what we're going to do with this today. We are now going to start drawing these Lewis dot structures as 3-dimensionally correctly as we can. So what can we do to make this look more like this? And guys, sadly, the answer is nothing. This is about as good as we can do drawing tetrahedral. We see the 4 points. We understand that they're actually spread out in 3-dimensional space. But guys, that is the way we're stuck drawing tetrahedral. So now let's go on to the next one. Guys, carbon dioxide, and you can see it looks like so. So guys, carbon dioxide, like so. So if you picture carbon dioxide, you've drawn this multiple times. We've got double bonds. We've got the extra electrons on the oxygen. We've got a molecule that looks something like this. And this is a completely legitimate way to draw carbon dioxide. What just fell? I'm guessing hydrofluoric acid. Yep, that thing rolls really easily. Okay, so guys, this looks like this. So let's talk domain and molecular geometries. How many domains on the carbon? 2. What's the domain geometry? Linear. And they're both bonding, so what's the molecular geometry? Linear. But guys, I know some of you, when you first saw this, said, what are you doing? But some of you actually draw them like this, and it's fine. This is right. But guys, I would propose to you that if we're going to draw this thing 3-dimensionally, this isn't the best choice. How come? It doesn't look linear. It looks bent. So guys, is this a valid Lewis dot structure? Absolutely. But if you were to draw this, I would suggest that what you should do, because this molecule is actually linear, is redraw it so it looks linear. Just a second. So guys, the idea here is now when we draw our Lewis dot structures, we want to draw them as much like they really look as we possibly can. Yeah. And so that's the little not change, but and it just means sometimes you may have to erase and redraw them. So let's try this. Water. So guys, looking at a water molecule, is it okay to draw water like this? Absolutely, because guys, that's a water molecule. So now let's talk about the domain and molecular geometries. How many domains on the oxygen? 4. Tetrahedral. How many of them are bonding? 2. So what's the molecular geometry? Bent. So guys, you understand that it actually looks like this. So is this okay? Yes. But is it best? And the answer is no. So what would be the best way to draw a molecule if it's bent? Draw it bent. So guys, that's the thing that you're going to be held accountable for today. While this is a completely valid Lewis dot structure, it's not best. And so it may just mean that you've got to erase and redraw to make them look more like what they really look like. You get the idea? Okay, so guys, let's do Nh3. And David, this is kind of what you were talking about. This looks like this. 4 domains tetrahedral, but 3 domains are bonding. So what is it? Trigonal pyramid. It looks like that. So what could we do to redraw this to make it more like what it really looks like? Nothing. That's as good as we're going to do. So let's try HCl. HCl looks like this. It really looks like that. What can we do to make that one better? Nothing. So what about this? CH2O. Guys, how many domains are on that central carbon? 3. So that would make it trigonal planar. How many are bonding? All 3. So the molecular geometry is trigonal planar. But guys, what could we do to make this one look better? And the answer is we can do something. Because what are the angles in a trigonal planar structure? 120 degrees. It looks like this. It looks like this. So guys, what I'm going to encourage you to do is draw it with those 120 degree angles. So if you've got something with a trigonal planar molecular geometry, draw it with a trigonal planar molecular geometry. You get the idea? So we're not doing anything new. We're simply building on what we understood, and we're drawing our Lewis dot structures best. Not just okay, but best, so it actually looks as much like it as it does as it can. That was a weird sentence. You get the idea? Okay, so now guys, next step in this process is we're going to step, and don't write any of this down, because I just lifted this out of notes from last unit. So guys, now what we're going to talk about is the 2 different types of covalent bonds that exist. We've already done this, but let's do this again. So guys, one of the types of covalent bonds that exist are what are called non-polar covalent bonding. And you may remember the way this works. If you've got 2 atoms of the same nonmetal, they share equally. And guys, we said it looks like this. So you've got 2 fluorine atoms. And remember when we talked way long time ago about they pull on each other and it's like mine and mine and mine and mine, and they're all pulling. So one fluorine pulls an electron, the other fluorine pulls an electron. They fight over these electrons. Which one of the fluorine atoms wins? Neither one. So they end up sharing equally, and this forms what we call a non-polar covalent bond. Do you remember that? Okay, so now guys, let's try this. What is called polar covalent bonding. Now we've got different nonmetals. So they're still nonmetals, so they're strong, but they're different. So they don't share equally, and they create what are called dipoles. And you learned this last unit, and I said don't worry about it. Well guys, now we're going to worry about it. So a dipole is a partial charge created by unequal sharing, and it looks something like this. Now we've got oxygen and fluorine. So guys, which one's going to be stronger, the fluorine or the oxygen if fluorine's on the right? Fluorine is stronger. So when these guys fight, fluorine steals from oxygen, oxygen steals from fluorine. But guys, look at where these electrons are. Closer to fluorine. Why closer to fluorine? Fluorine's stronger. So when these guys close down, it turns out that the electrons are actually closer to the fluorine than they are to the oxygen. Now guys, here's the trick. What is the charge of electrons? Negative. So what that does is it makes the fluorine slightly negative, and it makes the oxygen slightly positive because these electrons are closer to the fluorine than they are to the oxygen. So this end is slightly negative, and that end is slightly positive.
So will the fluorine have a -1 charge, or is it less than that?
No, and that's the trick. So if it was a -1 charge, that would be an ionic bond, right? Because if the electron is completely transferred, this would be -1, this would be +1, and that would be an ionic bond. So fluorine isn't strong enough to steal, so it's not ionic, but the electrons are shifted in that direction, making this partially negative and partially positive. So you could think of this as being like -0.1. And this is like +0.1. So it's not a complete charge, it's a partial charge. Yeah?
Are the dipoles what keep the 2 atoms together, or are they just
Good question, and the answer is no. The dipoles do not hold, you can't explain the strength of a polar covalent bond based upon their charges. The strength of the bond is still dependent upon the sharing, but the result of the unequal sharing is the partial charge. You guys okay? So guys, this is the new stuff. Here's what we're going to do with this today. Again, you don't need to write it down. We'll bring this all together in a minute, but here's what we're going to do. You guys understand that when we draw Lewis dot structures, we don't draw dots, we draw lines to represent these things. But guys, what we're going to do is we are going to represent the dipole like this. This is what you're doing today. Guys, when you represent these polar covalent bonds, what you're going to do is you're going to represent them with an arrow. And guys, this arrow points in the direction that the electrons move. So this arrow will always point at the more electronegative atom. So fluorine is stronger, so the electrons move towards the fluorine. So if the electrons move towards the fluorine, what's the charge of this side? Negative. And that means the charge of this side is positive. And guys, look at how we represent that. What we do is we cross the end of the arrow, and that makes a plus sign. So this end is positive, that end is negative, because the electrons move in that direction. You get the idea? So guys, that's what we're going to be doing today. But as I mentioned earlier, when we draw these things, what we're going to do, it won't let me do it. Guys, what we're going to do is we're going to replace the dots with a line, and now we're talking Lewis dot structures. And so guys, the electrons will always move. Holy smokes, what's going on? So guys, the electrons will always move towards the more electronegative element. We represent that with an arrow crossing the side, that end, because that end's positive, and then we'll of course represent our bonds with lines. So what are we going to do with this? Well, guys, we're now ready to talk about the practical stuff that you're going to start doing today. So here's what you're going to do, and you want to write down these steps. This is where you need to start taking notes again. We're almost done. I think you guys are going to like this. It's not too bad. So guys, these are the instructions for your homework assignment today. Step number 1 is going to be this. You're going to draw Lewis dot structures, just like the last test. But now you are going to draw them as realistically as possible. What's that? If you'd like to. I mean, if you want to have this as a reference. And so, guys, again, we covered that idea. If something's bent, draw it bent. If something is linear, draw it linear. If something is trigonal planar, draw it trigonal planar. Now, guys, step number 2 is this. You are going to draw polarity arrows for each one of the bonds. Those are the arrows that I just showed you. The arrow always points towards the more electronegative element because the arrow represents the direction that the electrons are moving. Then, guys, step number 3, and this is the big idea for today, you are going to figure out if the molecule is polar. Because, guys, it turns out polar bonds don't necessarily make polar molecules. So guys, we've been working together now for almost 18 weeks. And by now you know that there's sort of a method to my madness, right? So you ready? How do you know if a molecule is polar? Well, guess what? You just need to ask yourself a simple question. What could that question possibly be? The question that you ask yourself at the end of the previous lab. Guys, it all comes down to symmetry. Remember how we did that in the last lab? And when you had the model kits in your hand, you were determining if these molecules were symmetrical by looking at the X, Y, and Z planes. Guys, that's why we had you do that. Because now you're going to use that concept of symmetry and apply it to the idea of polarity. So I know this doesn't make sense yet, but just watch. So the idea is this. If a molecule is balanced or symmetrical, it is nonpolar. And all you're going to do is underneath it, you're going to write down nonpolar. Now, what if a molecule is non-symmetrical? Well, if a molecule is non-symmetrical, it is then polar. And then what you're going to do is use another arrow to represent the overall polarity of the molecule. So guys, these are the instructions for your homework today. We are going to go back and look at the 6 molecules that we looked at a moment and talked about how to represent them best. And we're going to identify their polarities. We're going to do that by drawing them best, then drawing in the polarity arrows for the bonds, and then talking about symmetry. So guys, we'll look at these 6 examples, then you'll have the remainder of the day. And it is a short day. Whoa. Oh gosh, holy smokes, that scared me. Ralph, do you know, are we single assembly scheduled today? Okay. So I looked at the schedule, but I looked at next Wednesday's schedule, and it says we're done in 14 minutes. I was like, oh crap. No, that's not the case. So guys, we're out at 8:55, so 10 minutes. You'll still get your homework done. You guys all caught up? Because when you're done with this, you're done taking notes. And then guys, well, sort of, I think you're going to benefit from going through this process, looking at examples with me. You guys all caught up? You're good? Okay, so let's do it. So guys, it goes like this. First of all, CCl4. Just really quick, scratch down its Lewis dot structure. Just copy it down. Make it fairly big though, guys. You're going to want to make this probably, I don't know, 3-4 centimeters across, 1.5 inches. Did I tell you about that when I tried to switch over to the metric system? It was a disaster. I took all the readouts in my truck and switched them over to metric. It was not good. I really wanted to, though. Just didn't work. I had to. I was going to get a speeding ticket. Right, but I was guessing. I was like, 80, that's got to be fine, right? In a school zone. And so then I'm doing the math in my half, trying to convert to miles. I'm like, 80 divided by 1.6. I don't know, it was trouble. I gave up. Okay, so guys, what we're going to do now, step number 1 is draw the Lewis dot structure as accurately as possible. So guys, what are we going to do to redraw this so it looks tetrahedral? Nothing. That's the best we can do. So now, guys, step number 2 is draw in the polarity arrows for the bonds. In order to do this, we need to know, and guys, this is why it was on the test. We need to know which atom is more electronegative, carbon or chlorine. That's why we ask you those questions on the test. Which of these 2 atoms is more electronegative? So which is more electronegative, carbon or chlorine? And guys, we got some problems because when we go down to chlorine, it gets weaker, but when we move to the right to chlorine, it gets stronger. So which one wins, down or over? Well, look it up. Guys, looking on the back, the electronegativity of carbon is 2.55, chlorine is 3.16, so chlorine is more electronegative than carbon. And so guys, here's what we do. What we're going to do is we are going to draw arrows along all of these bonds pointing towards the more electronegative chlorine and showing that literally carbon is being ripped apart by chlorines. Those chlorine atoms are stretching the carbon in all 4 directions because chlorine is stronger than carbon, and literally this is being stretched like Stretch Armstrong in all 4 directions. Go ahead, Cam. However, it's up to you. Yeah, I like to do them like that. You get the idea? Okay, now guys, we understand that carbon is now being stretched in all, well here, carbon is now being stretched in all 4 directions at the same time by the chlorines. Now here's the question. Is the molecule polar? We know the bonds are polar, but is the molecule polar? And the way to know is symmetry. Is this molecule symmetrical? It is. Guys, let me grab a ruler and let me show you. So guys, it goes like this, X, Y, and Z plane, right? So is it symmetrical about this plane? Yeah, 2 chlorines on each side. How about this plane? Yep. How about this plane? It is symmetrical. So guys, this molecule is symmetrical. Here's what that means. It means that all of the poles cancel out. If you've taken physics and you understand vector sums, that's what we're talking about here. That this pole, this pole, this pole, and this pole all cancel out. Now guys, if you don't understand what I'm talking about, picture it this way. Imagine if we could tie 4 ropes to this. And if we could pull this direction, and this direction, and that direction, and that direction. If we could pull all 4 of these directions with the same force, would the black ball move? It would not, because all of the forces cancel out. It's symmetrical. Again, if you've taken physics, the vector sum is 0. So guys, what that means is that while these bonds are polar, the molecule is non-polar because all of the poles cancel out. But if that's mucky in your brain, all you got to know is symmetry. Is it symmetrical? Yes. And you're good. If it's symmetrical, it's nonpolar. Let's look at another example. So guys, oh gosh, I didn't want to do that. So guys, the next one we're going to look at is carbon dioxide. But before you draw it, let's talk. What can we do to draw this more accurately? Nothing, right? Because this is linear. 2 domains, both bonding, it's linear. So let's draw it linear. Yeah, when we get to H2O, you'll see I'm going to throw you a curveball. So guys, we've got carbon dioxide. And it is drawn best. It is drawn as realistically as we possibly can. So now what we need to do is draw in our polarity arrows. How do we know which direction the arrows point? Electronegativity. So guys, which is stronger, oxygen or carbon? Yeah, that's just a simple trend, right? Oxygen is to the left of carbon. So this would then be polar. This would then be polar towards the oxygen, and this would then be polar towards the oxygen. Now let's look at the molecule. Is this molecule symmetrical? Oh yeah, guys, look. This is definitely symmetrical, right? So if it's symmetrical, is it polar? No. This is non-polar. Now guys, if you don't understand that, maybe if you look at this, you'll see it. Because this oxygen's pulling that way, this oxygen's pulling that way, but those 2 poles cancel out, and therefore it's non-polar. Ooh, I just had an idea. Would it have been better to do carbon dioxide before CCl4? Is it easier to see how the poles cancel in this than it is in CCl4? I'm going to switch these. I think it would be better to do this one first. Yeah. Mm-hmm. Yeah, right. Correct. And so it would be nonpolar. We're going to look at an example. It's not symmetrical because what you're talking about when you mean bromine, right? Yeah. So like for example, what about this? Let's take this molecule that we've said is symmetrical and let's replace it with a hydrogen. Now this is no longer symmetrical because if we draw the plane of symmetry this way, this is, can I grab it like, I don't know, like this? So if we draw the plane of symmetry this way, this is a hydrogen and this is a chlorine, and those are not the same atoms, so it's no longer symmetrical. It has to be the same atoms. Yeah, absolutely. Great question. You guys good? Okay, so let's do another one. So guys, the next one that we're going to look at then is water. Don't draw. Water, right? Is this an okay way to draw water? Yeah. But is it best? No. So guys, water actually would be better drawn bent, largely because it's bent. Okay, so now guys, let's draw in the polarities for the bonds. If you look up their electronegativities, you find out that oxygen is like 3.4, hydrogen is 2.2. So which direction is the arrow going to point at, the oxygen or the hydrogen? The oxygen, because it's stronger. So this arrow goes this way, and this arrow goes this way. Now guys, the big question, is this molecule symmetrical? No. So now guys, check this out. Watch my hands. So this molecule is not symmetrical. So what we need to do now is figure out the polarity of the molecule. And for those of you that have taken physics, this should start to sound familiar. Because guys, here's the idea. This bond, let me switch hands. This bond is pointing this way, and this bond is pointing this way. So what is the sum of up and left? So we're going up, we're going left. What's the sum of up and left? It's diagonal. Get the idea? So guys, this molecule is polar in that direction. So if you have a molecule that is non-symmetrical, you are going to figure out how all the arrows line up. And that will be the overall polarity of the molecule. Only for the polar ones, because for these, they don't have overall polarities, because they all balance out. Yep. And guys, again, if you've done physics, those are vector sums. But you ready for this interesting idea? Let's just do this really quickly. So what? What does it matter that these top two molecules are nonpolar and water is polar? Well, guys, here's the answer. Water is a liquid. These two substances are both gases. And it's all because of their polarities. And we're going to talk more about that after Christmas. Yeah, Nate? Okay, so the idea is this. Wait, the red arrows? These guys. Okay, so these red arrows, the bond polarities, always point at the stronger atom based on electronegativity. So look, and it's on the back of your table. If you look up the electronegativities, oxygen is 3.44 and hydrogen is 2.2. So these bond arrows always point at the stronger atoms. And then the overall polarity is the sum of them. Is that okay? Not directly. It correlates with size. Yep. Okay. So, guys, oh no, stop doing that. Let's do this one. Nh3. Can we draw it better? No, it's trigonal pyramid. That's the best we can do. So now, guys, we need electronegativities. Nitrogen, 3.04. Hydrogen is 2.2. So nitrogen is 3. Hydrogen is 2.2. So Nate, which direction will the arrows go if nitrogen is 3 and the hydrogens are 2.2? Towards the good, inside. That's a great way to think about it. They go inside. They point towards the nitrogen. Quite literally, they go inside. It sucks the molecule together. So now, guys, what's the last thing to do? The overall polarity of the molecule is Nh3 symmetrical. It is not. So what direction do the arrows go? So, guys, what is the sum of in and up? Up. So the overall polarity is that. By the way, guys, NH3 is ammonia, and that's what makes this such a great cleaner. Because ammonia molecules are polar, they're really good at ripping dirt apart. Yes, and not only that's the most important thing you're going to do is draw that overall arrow. Yep. Two more. Oh, go ahead.
So how do you kind of like determine symmetry based off of a two-dimensional shape?
Because you actually know what they look like three-dimensionally. And that's the whole point. And again, that's why we put that section on the test, is because we need you to be able to picture these three-dimensionally. And you should be able to look at this and go, that's trigonal pyramid. And I can sort of, even though it doesn't look fully trigonal pyramid, I understand that that's what it is. All right, so guys, next one, HCl. So which one's more electronegative, the chlorine or the hydrogen? Chlorine. So guys, the arrow goes like that towards the chlorine. Is it symmetrical? No. Now we need to draw in the overall arrow. It's the same. So guys, because this molecule only has one bond, the polarity of the bond is the polarity of the molecule. For those of you that don't know, HCl is hydrochloric acid, which is stomach acid. And that's why HCl is so good at ripping your food apart, is because of its polarity. So why doesn't HCl rip your stomach apart? Yeah, good. You've got a mucus lining on the inside of your stomach that protects your stomach from its own acid. What's it called when that mucus lining gets holes in it? Ulcers. That's what ulcers are. You're actually literally digesting your own stomach. All right, guys, last one. CH2O. And you'll notice that I drew it as realistically as possible. We already did this before, but the idea is that this is trigonal planar. So let's draw it trigonal planar. Now, guys, we need to draw in the individual bond polarities. So I'm going to just scratch the numbers down. So hydrogen is 2.2, carbon is 3 point what? I don't know, 4? No, 2.5. So guys, carbon is 2.55. And then oxygen is 3.44. Okay. So guys, now we got to figure out these bond polarities. So carbon is more electronegative than hydrogen. So this one goes this way. So does this one. And then oxygen is more electronegative than carbon. So this one goes this way. So guys, obviously this isn't symmetrical. So guys, what's the overall movement of in and right? Right. And that would be the overall polarity of the molecule. Not too bad, right? But guys, the thing that's interesting about this is, in as much as this is interesting, you're starting to get a little flavor for how this stuff has really far-reaching implications. Stomach acid, cleaners, gases, solvents, you name it. Carbon dioxide's a gas because it's nonpolar. Guys, we're going to talk about all that stuff after Christmas. So you have in front of you your homework. Guys, there are 14 Lewis dot structures to draw. Remember, draw them as realistically as you can, which may mean that you need to do some erasing. Then, guys, notice what you're doing along the way. And this is the last time this is going to happen. But I am going to ask that you please, you know what, let's do this. See the directions where it says domain and molecular geometries and angles? Cross out domain geometry and cross out angle. All I want to see from you, but you got to know those, right? But you really need to know the molecular geometry. So guys, please write down the molecular geometries and then all the polarity arrows for the bonds and then the polarity arrow for the molecule. And then guys, there are 14 of those, and then you've got 6 additional questions to answer. Don't do the questions before you do the 14 examples, because some of the questions are about the examples. And guys, we will not grade this on Tuesday. We will grade this afterwards, second camp. And then when I see you right after on Tuesday, we will give you your test back. We'll analyze those. And then, guys, Rudolph the red-nosed reindeer. Go ahead, Ken. No, so I just want to know that you know the molecular geometries. Okay, you guys good? Okay, so I'm going to stop recording, and then I'm going to post your test scores. But guys, here's the thing. Hold on, here's the hazard. Let me stop recording.